When a skyscraper collapses, the structural failure rarely begins with the thousands of tons of steel pressing down from above. The flaw usually lies in the one place no one bothered to look, the earth below. To prevent this, engineers perform site exploration. It is a thorough investigation of the subsoil conducted before the foundation plans are even prepared, designed to determine the properties of the underlying material at a construction site. This requirement exposes a physical paradox in construction. The single most critical load-bearing component of any project, the natural earth itself, is the only layer that engineers cannot naturally see or measure from the surface. Without this exploration, a builder has no way to calculate if the earth can support the structure's weight. To build safely, engineers must first map the geology of the area. Engineers approach site exploration as a targeted mission to answer 6 critical questions before construction begins. The first 3 goals focus on the immediate build, determining the soil's safe bearing capacity, selecting an economical foundation type, and fixing the exact depth that foundation must reach inside the ground. The final 3 goals move into prediction. Engineers calculate the likely settlement of the structure, locate the underground water level, and forecast any specific difficulties the subsoil might cause during the construction phase. Extracting this data requires a specialized arsenal of physical exploration methods. The choice of tool depends entirely on how deep the engineers need to drill and the density of the earth they expect to encounter. These 6 parameters form the technical framework for the project. They provide the measured data needed to ensure the building remains stable and upright under its intended load. The process begins at the surface with inspection. Engineers study the immediate surroundings, examining neighboring quarries, existing structures, and the exposed strata in local wells to observe the nature of the soil at different depths. They scan for surface indicators of instability. They check if the ground is waterlogged or marshy, assess the risk of ground movement from nearby slopes, and verify if the subsoil water contains chemicals that could damage the foundation. Moving below the surface, the most direct method is the test pit. This involves digging a hole large enough to permit the entry of persons for direct visual inspection of the substrata up to a depth of 3 meters. This cross-section shows the horizontal layers of clay, sandy clay, and gravel visible in a standard pit. The excavation geometry is dictated by the soil type. In cohesionless soils, the sides are sharply sloped, while cohesive soils below 3 meters require vertical bracing for safety. For a rapid diagnostic in soft soils, engineers rely on probing. A pointed steel bar, 25 to 40 millimeters in diameter, is driven into the ground by a drop hammer. Experienced workers judge the underlying strata by reading the bar's penetration rate. The number of blows required to drive the rod deeper provides a rough idea of the soil's resistance at various depths. These manual methods provide excellent localized data, but they are limited by human reach and the inability to penetrate dense, highly compact earth. When exploration must exceed 3 meters, the process moves to mechanical boring. This diagram illustrates the post-hole auger, used in clay or sandy soils. Rotating its handle drives the corkscrew-like tool into the ground. For every 30 centimeters of depth, it is extracted, and soil samples caught in its threads are collected for analysis. In soft to stiff cohesive soils where simple augers fail, engineers deploy wash boring. This schematic shows wash boring equipment. An outer casing pipe is driven down, housing a narrower jet pipe. Water forced down the jet pipe under pressure displaces material at the base, pushing a slurry up the annular space for surface collection. Wash boring allows for rapid, deep penetration, though it requires engineers to interpret the strata by observing the rate of progress and the changing color of the expelled slurry. Eventually, the drilling hits a barrier, underground boulders or solid bedrock. At this stage, fluid pressure and rotational leverage are no longer effective. The solution is percussion boring. This method breaks up the substrata through repeated, heavy mechanical blows from a chisel. The pulverized rock is converted into a slurry with water, bailed out of the hole, and dried for examination. When engineers need to see the exact composition of these hard layers, they use core drilling. This method uses a rotating hollow steel tube equipped with a diamond or shot cutting bit at its base. The bit makes an annular cut through the rock, leaving a solid cylindrical core inside the tube. This provides an undisturbed sample of the deepest, hardest formations on the site. As the Earth's resistance increases from soft clay to bedrock, the engineering methods scale from manual inspection to high-pressure mechanical drilling to extract the necessary data. Back on the surface, the physical samples, slurry, clay, and rock cores, are analyzed and translated into engineering specifications. These samples answer the initial questions. A solid rock core confirms the soil's safe bearing capacity, while a wet auger sample determines the depth of the groundwater level. By synthesizing this data, engineers create a volumetric map of the site. The building is designed not just for its own weight, but in direct response to the specific measured profile of the soil layers beneath it. Site exploration replaces subterranean guesswork with measured data, providing a verifiable geological profile of the site. We now have a clear picture of the materials under the surface. But the next stage is to apply force directly to those materials, testing the soil to mathematically define its breaking point.